Hi, this is Sudeep Manchanda from Quite Easily Done. This video is a part of this series Know Your Components, and we would be talking about the 555 timer. In this video we would cover what is a 555 timer. We would understand the internal composition, the internal circuitries of a 555 timer, and then we would look at the three modes in which a 555 timer is mostly used. A 555 timer is an 8-pin IC which is used mostly to create circuitries like oscillators, a delay circuit, or a flip-flop. Unfortunately, these days, with the coming of controllers like Arduino, which is cheap and easy to program using programming languages like C++, a lot of enthusiasts use them to create very simple delay circuits or the oscillator circuits that we are talking about. Unfortunately, even though it is easy to use without having to understand electronics, it increases the cost at least by 100 times as compared to if you would be using a 555 timer. A 555 timer is not very difficult to understand. Once we do it, we would be able to use it appropriately in places where we are able to simplify our projects, make it very cheap and effective and reliable also in a lot of cases. So let's first look at the pins that are there in a 555 timer, and then when we come up to the understanding the three modes in which it operates, we would better understand its applications also. So 555 timer is the 8-pin IC in which there are two pins, the pin 1 and the pin 8, which are the VCC and ground, basically the power supply to the IC. When we are looking up at the IC, there is always this small circle or dot. This is applicable for any IC that we look at. That is where we start numbering the pins. So it goes down pin 1, 2, 3, 4 and then goes up again 5, 6, 7, 8. That is how any pin is identified, and that is we would be needing that before we are connecting the IC into any circuit. So the two pins that we first talked of are the ground and the power supply. Then there is a pin which is to reset the state of the 555 timer. There is an output which is fed to our driving circuit, whatever we want to drive through this. Then there is a trigger and a threshold. These are two controlling inputs to the 555 timer which would define its behavior. We also have discharge. This pin is used to discharge any external capacitors that you would be using in the circuit, and a controlling voltage to kind of have some delta offset if you need to require that. So let's first look at the internal composition of a 555. So this is an internal diagram of a 555 timer. If we look, between the ground and the power supply, there are three 5 kilo ohm resistors, and that is why the name 555 comes in. It represents the 5 resistors that are there in between. So before we are able to understand the working of a 555 timer, we would have to break it down into its constituting components. The first of which is the three resistors which are there in between the ground and the power supply, which is what we are calling as the voltage divider. So we have three resistors of equal values between ground and a voltage V. This circuit is called a voltage divider, and the reason why it's called a voltage divider is at different stages, like let me say point 1, 2, 3 and 4, there will be different voltages that would be there, which is in proportion to the resistance values that is there in it. So we know Ohm's law says I is equal to V by R. In this case, the current flowing through all the resistance I would be equal to the voltage applied across it divided by 3R, because there are three resistances in series over here. And if we look at the voltage at point 2, it would be equal to the voltage drop across the resistance R, the just one resistance. So we know the voltage V is equal to IR. In this case, V is V divided by 3R into the resistance value R, which gives us 1 by 3 V. Or if this is VCC voltage, then it's 1 by 3 VCC. Similarly, the resistance at point 3 would become 2 by 3 VCC. So this is what we have to understand, and this is kind of what we're trying to achieve, is using the voltage divider, is to get a 1 by 3 VCC and a 2 by 3 VCC at point 2 and 3 in the circuit. So if we go up, we have understood that here we have a 1 by 3 VCC, which means at the comparator over here the input is 1 by 3 VCC, and over here the input is 2 by 3 VCC. The second component of the 555 timer is the comparator. We had looked at the op-amp as a component during our understanding of the know your component section. Very quickly telling up in brief, is an op-amp is a linear amplifier which has two inputs in it, which is the negative and the positive, or the inverting and the non-inverting terminals, and it has an output. In the configuration that it is used over here, the output kind of says is the positive terminal greater than the negative or not. So let's say I apply 1 volt on the inverting terminal and 2 volts on the the non-inverting terminal. I would get is output as a high. If my power supply to the IC is 5 volts, this would mean 5 volt. And similarly, if my voltage is, I swap it, I make the voltage on the inverting terminal as 2 volt and the non-inverting terminal as 1 volt, my output would become, if I'm applying a supply of plus 5 and ground, the output would in that case become 0 volt. So in order to understand this in detail, you can refer to the Know Your Components video for op-amp, the operational amplifier. So that's the second component. So we have talked of the voltage divider, we have talked of the op-amps, the comparators, and then the final is the SR flip-flop. The SR flip-flop is a circuit which is the SR latch over here, which has one input which is called R, or the reset, and the other input which is called the set. It gives us an output Q and Q naught, which is not of Q, basically the opposite. The table over here explains how an SR flip-flop works. If I'm not giving any input to the S and the R, then there are no changes in the state. So if the Q output was 1, it will remain as 1. If the Q output was 0, it will continue to remain 0. If I give S as 1, which is I'm trying to set the latch and keep the R reset thing as 0, it would make Q the output equal to 1, irrespective of what the previous state was. Similarly, when I put the set input as 0 and the reset pin as 1, it will always make the Q output as 0. It will reset irrespective of what the old state was. And the output 1 and 1, the input 1 and 1 to the both the S and the R inputs of an SR latch is, we call it as an invalid input. We never use it. Okay, so now that we have seen the individual components, let's put them together and understand what does it mean in case of a 555 timer. So let's see. So let's look at the first comparator, the comparator 1, which is on the left. It has an input which is 1 by 3 VCC. VCC is the voltage that is applied to the power supply. If I give in a trigger over here which is less than 1 by 3 VCC, it would make the S as 1, because the comparator would compare 1 by 3 VCC being higher than the trigger. It would give the comparator will give a 1 output which goes to the set, which would make the output as 1. The output O would become 1 in this case, and high, which is what we get in the output. And interestingly, what happens in that case is, because we see the NPN transistor, which we said can also be used as a switch, it will cause a discharge of the external capacitor to the ground over here. Similarly, let's look at the other comparator, which has an input of 2/3 VCC on the inverting terminal of the comparator 2. So if I give a threshold over here which is greater than 2/3 VCC, it would cause the second comparator to give an output of 1, which would reset the flip-flop, making the output go 0 and 0, and would disconnect the discharge from the ground. So now the external capacitor would not be discharged but would get charged. So this is what internally happens in a 555 timer in a simple way. By using these configurations, we can use the 555 timer in one of the three modes. One is called a bistable mode. A bistable mode means that the output of the 555 timer can remain stable in both 0 and 1 state. Which means if I give in a trigger to bring the state of the output of the 555 as 1, it would remain as 1 always, till when I don't give a reset input and bring it back to a 0 state. So it will be able to remain stable in both 0 and 1 status. Then we have is the monostable state, in which it is stable only in the 0 state. So if I'm in the 0 state, I use the trigger to bump up the output to a 1 like this in a pulse, it will come back to 0 after a while. It will fall down back to 0 depending, and after how much time will it come back to the 0 state would depend on the resistance and capacitance values that we would be looking. So this is a monostable mode. This is how we use it as a delay circuitry. So you will get a small input pulse. This is your input, but the output of a monostable, what you will get is, we will look at that when it's triggered, it will remain on for a while and then come back to 0. That is a monostable. And then you have is an astable state. And astable is where it will remain stable in none of these states. So when it is 0, it is an unstable state for a 555 timer. It will go up to a 1. It will remain in 1 for a while, and because it's also not a stable position, it will come back to 0. Again, after a while, it will turn back to 1, then 0. And this is how we would use a 555 timer as an oscillator. So we're kind of creating a pulse train over here. We are causing so this is like an oscillator, an astable mode. A monostable mode is being used as a delay circuitry, and a bistable mode is being used like a latch or a memory system. So let's look at the three modes by looking at the boards that we have created to better understand what these actually do. So I have here three boards that I have created, one representing the monostable mode, the other astable, and then the bistable modes. So the one that we see over here, if you can see, the LED is going on for a while, going off again, and then remaining off for a while and then going on again. That is the astable mode, where neither the 0 or the 1 state for the 555 timer is stable. It's toggling between the two, it's acting like an oscillator. Then I have over here in the bottom is the monostable, where I have this button which I will use to trigger. When I trigger, the output becomes 1, and this 1 output will remain 1 for only a while, and while that is in the 1 state, where it will fall back again to 0. So there it is. The time it takes for it to time it can remain stable in the 1 state would depend on the capacitance value over here and one of the resistance over here. Similarly, the capacitance and the resistance over here will define the frequency at which the blinking is happening. Finally is the bistable mode, where the output can remain stable in 1 and 0 both. So right now this LED over here is in the 0 state, it is stable. When I provide a trigger, it comes to a 1 state. Now this 1 state would remain there till when I don't go to the reset button and reset it. So that's the bistable, where it will remain stable in 1 or can remain stable in the 0 status. The monostable one is where I give in a when I give the trigger, it goes to an unstable 1 state, will remain over there for a while and come back to the stable 0 state. And astable one is where it's neither stable in the 1 or the 0 status, it will keep toggling between the two of them. The frequencies of these will depend on the value of the resistances. To look at the details of how these boards have been created and their working and explanation, we look at the Know Your Board section where these have been explained. Thank you. If you have any questions, please let me know. Give your comments, like us and subscribe us. And if there are any other videos that you want from us, please let us know. Thank you so much.